Hi there, it's Miss Heaton signing in to talk with you about standard reduction potential calculations. Hopefully you already have this handout from your teacher. If not, you'll want to write everything down as we go through an example of how to calculate voltage and draw a cell, and then I give you one to try on your own. We're going to dive right into this first example problem that's written on your sheet. Now, it could either be written like this or in words. Either way, you should be able to interpret it and know that it means the same thing. So we've got a copper and copper plus 1 ions and zinc 2 plus ions in our cell. Now, your sheet doesn't say this, but we know that anytime you have a positive ion, it has to have an anion to counteract it. So let's say the copper plus 1 is paired with the nitrate ion, and the zinc 2 plus is paired with the sulfate ion. That won't come in handy until later. Okay, so the first thing you want to do is write out the reduction reactions based on the standard reduction potential table that you have and find their corresponding voltage. So copper plus and 1 electron makes copper, and you can find this on your table that it has a 0.52 voltage. Please try that. Make sure you understand where that came from. The zinc 2 plus would be reduced into zinc and would have a negative 0.76 voltage. The next thing you do is decide which one's oxidized and which one's reduced based on their potentials. The one that has a lower voltage will be flipped to the oxidation reaction. The one with a higher voltage, the one that has a higher voltage will stay as is. So since zinc has a lower potential to be reduced, it will be oxidized. So we rewrite the reaction with products becoming reactants and the reactants becoming products. And the sign on the voltage becomes positive. So now this half reaction no longer exists. We are going to look only at the second half reaction that is now oxidation. Step 3 is to determine the overall reaction by adding the two half reactions together, making sure that the electrons cancel. If they don't, we have to double or triple or whatever one of those reactions. However, this is different than like Hess's law because we don't change the voltage. The electric potential, the potential to be reduced, does not change. So this is how it would look. You would write copper 2 plus, copper plus 1, and there's 2 of them, and 2 electrons turn into 2 coppers and still have the same voltage, whereas zinc turns into zinc 2 plus and 2 electrons and has the same voltage. Then we would do just like we did with balancing redox reactions. We would cancel out anything that appears on both sides, which will typically just be the electrons, to get the overall reaction, and then add up the 2 voltages to get the overall voltage of the cell. So 1.28, that's almost as good as a regular AA battery, so that's not bad. Now, what information can we get from what we've talked about so far? First of all, you should know that electrons will flow from the thing that's oxidized, in this case the zinc metal, to the copper metal. We know that at the anode is where oxidation occurs, anox. We know that reduction occurs at the cathode, red cat, and that electrons are going to flow from the anode to the cathode. This is all kind of a review of what Ms. Ewald talked about. I'm just making sure you know these important details. We also know that electrons flow towards the positive charge side because they're going to be attracted to the opposite charge of themselves. And we know that the electrons moving through the wires have to be balanced by the movement of ions. So any anions that are not already at the anode will move towards the anode to replace the electrons that are leaving, and cations that are not already at the cathode will move through that salt bridge, through the U-tube, to replace the positive charge that's lost when the cathode is reduced. We also know that the thing that is being the thing that's being reduced is going to gain mass as the ions turn into solid metal, and the thing that's being oxidized will lose mass. Maybe we should write that in. Reduced means it gains mass, oxidized means it loses mass, and we saw that in the in-class animation. Okay, now the important part. Let's draw up this cell based on all that information that we know. So you start by drawing a beaker, and I'm not the greatest artist, so you don't need to be either. We start by drawing 2 beakers connected by a salt bridge. And in one is a metal, in the other is the other metal, and we will connect them with a wire. Let's see what we could also label here. We said that copper was being reduced, and so that is our cathode. And I like to draw my cathode on the right and my anode on the left. So let's label the copper at our cathode, and in our beaker we'll have copper ions, as well as, remember up here at the beginning when I said we had to talk about the copper being balanced by something negative? Let's put nitrate ions in there. There'll be nitrate ions. And over at our anode, we had zinc metal, Zn electrode stuck into zinc ions in solution, and the zinc ions, remember from the beginning, were paired with sulfate ions. What else can we label? Well, we know that at the anode is where oxidation occurs, and at the cathode is where reduction occurs. We also know that the anode is negative, that the cathode is positive. We know that the electrons will flow from the negative anode towards the positive cathode, so that would be where the electrons are flowing. Let's talk about the salt bridge and how things are going to flow through that salt bridge. We know that anions go towards the anode, but specifically, what are the anions that will go that way? Well, if we look at our container over here, there's nitrate ions that could flow towards the anode, so the anions that would flow here would be nitrate. The copper 2+ ions would not go that way, and the sulfate ions are already there, so we couldn't say the sulfate ions are going anywhere. They're just staying put. On the other hand, let's talk about our cations that will flow towards the cathode. The cations in the other side are zinc 2+, so they could flow towards the copper half cell. The copper plus ions are already there, so they're not going to flow towards the cathode. They're already at the cathode. So that would be all of the things that are flowing. Maybe one other thing we could label is what's losing and gaining mass, as we talked about up here. We said the copper electrode, which I didn't draw the bottom of, the copper electrode is going to be gaining mass, and the zinc electrode over here is actually going to be eaten away at. It'll be losing mass. And we could also label the half reactions that are occurring at each. Zinc is turning into zinc 2+ and 2 electrons, and copper plus is combining with an electron, gaining an electron to turn into copper ions. Oops. Please ignore the sound of the bell. Okay, folks, that's basically what we're going to be doing. We're going to be practicing this for several days. And what I want you to do right now is try this with a different pair of electrodes. Let's try it with gold and gold 3+ and chromium 3+. Write your own equation for the half reaction, follow all these directions, and draw a picture similar to what we did here. You're going to need to use your reduction potential table, so if you don't have it, look it up online, bring that to class, and we will continue to discuss. Happy volting, I don't even know if that's a word. See you later.